Imagine stepping outside tomorrow and finding the sun nailed to one point in the sky. It never rises, never crosses overhead, and never sets. On the far side of Earth, billions of people wait for a dawn that never comes. Earth has become tidally locked to the sun. One rotation now takes exactly one orbit, so the same hemisphere always faces the star. This cannot happen naturally to modern Earth before the sun dies. At our distance, solar tides are far too weak to break the planet in time. So this is a controlled thought experiment. Earth slows without being shattered. Its orbit stays near 1 astronomical unit, and the atmosphere and oceans survive the transition. The question is not how the break was applied. The question is what happens after the climate settles. The popular answer is a planet cut cleanly in two, an incandescent desert under permanent noon, and a frozen wasteland under permanent midnight. That picture is memorable but incomplete. Air moves. Water moves. Clouds reflect sunlight. Once those three systems begin carrying energy away from the bright hemisphere, the sharp line between furnace and freezer starts to blur. Tidal locking means synchronized motion, not a motionless planet. Earth would still turn once during every trip around the sun. That single yearly rotation is exactly what keeps one longitude pointed sunward. If Earth stopped rotating completely while continuing to orbit, every location would still receive 1 day and 1 night per year. A truly locked Earth must rotate once every 365 days. The sun-facing point is called the substellar point. Here the sun hangs overhead forever. Surface rock and ocean absorb continuous energy, warming the air until it rises. The pressure pattern pulls cooler air inward near the ground, while warmer air flows away at altitude. Instead of familiar east-to-west weather, the planet develops a giant circulation cell organized around one permanent hot spot. That circulation is the first reason the nightside does not automatically lose its entire atmosphere. In 1997, Manoj Joshi, Robert Haberl, and Robert Reynolds modeled synchronously rotating terrestrial planets in Icarus. With Earth-like stellar energy, atmospheric collapse required very thin air. For carbon dioxide and water vapor, collapse appeared near 30 millibars, only a few % of Earth's sea level pressure. A dense atmosphere transports heat far more effectively. Later three-dimensional models made the result even stranger. Jun Yang, Nicholas Cowan, and Dorian Abbott found in 2013 that slow, synchronously rotating worlds can build a bright shield directly beneath their star. Permanent heating produces permanent convection. Convection produces thick clouds. Those clouds reflect so much incoming light that the place receiving the most sunlight can protect itself from overheating. On modern Earth, clouds come and go with moving weather systems. On this world, the stellar target never moves. A towering cloud deck could remain anchored above the substellar ocean, bouncing sunlight back to space day after day. Yang's simulations found that this stabilizing cloud feedback could allow liquid water under stellar fluxes, much higher than older one-dimensional models predicted. Permanent noon can manufacture its own parasol. The ocean becomes the second planetary conveyor belt. Warm surface water flows away from the dayside, while colder water returns below. The exact result depends on continents, ocean depth, salinity, and whether sea ice drifts. That uncertainty matters. In 2020, Jun Yang and colleagues showed that moving sea ice can export frozen water into the warm region, where it melts, potentially shrinking the open ocean and pushing some locked worlds toward a snowball state. So there is no single map, of a tidally locked Earth. Put a continent beneath the fixed sun, and you may create an enormous dry interior. Put the Pacific there, and you may create a bright, stormy ocean surrounded by ice. Change the carbon dioxide level, and the liquid region expands or contracts. Climate models do not produce one inevitable twilight paradise. They produce competing states controlled by air, water, geography, and ice. The night side would still be brutally cold. There is no direct sunlight, plants cannot photosynthesize normally, and snowfall can accumulate without a summer melt season. But with a substantial atmosphere, it need not approach the temperature of empty space. Atmospheric dynamic simulations by Edson and colleagues found nightside surface temperatures near 240 Kelvin in Earth-like locked aquaplanets. About -33 Celsius, hostile but not an air-free abyss. Water creates a slower danger. Snow and ice falling on the dark hemisphere can become trapped there. Over thousands of years, glaciers may pull water away from the illuminated ocean and store it in a permanent nightside ice cap. Geothermal heat and glacier flow resist that trap, while ocean circulation returns some energy. The final balance is a research problem, not a settled fact. Between permanent day and permanent night lies the terminator, a ring where the sun sits on the horizon. It is tempting to call this the habitable zone of the planet, a narrow country of endless sunset. But the best location depends on the atmosphere. Efficient heat transport can make large parts of the dayside temperate, while a thin atmosphere might leave only a small border region survivable. Life there would lose the clock that shaped almost every ecosystem on Earth. No sunrise triggers flowers. No sunset releases nocturnal animals. Circadian rhythms could persist internally, but the sky would never reset them. Agriculture would migrate toward artificial schedules, controlled lighting, and regions where temperature and water are manageable. Longitude would become climate. Moving east or west could replace moving from equator to pole. The wind would also redraw civilization. Near the surface, air tends to converge toward the warm dayside. Higher up, it returns toward darkness. The details depend strongly on rotation rate and topography, so claims of a single planet-wide hurricane are not justified. But weather would be persistent. Storm tracks could remain in similar places for generations because the energy source beneath them never moves. This scenario is imaginary for Earth, but not for the galaxy. Planets in the habitable zones of cool red dwarfs orbit close to their stars, where tidal forces are powerful. Rory Barnes calculated in 2017 that tidal locking should be a major part of the evolution of many potentially habitable planets. NASA considers all 7 known TRAPPIST-1 planets likely locked, with orbital periods from roughly 1.5 to 19 days. That changes how astronomers search for life. A locked planet should not be rejected merely because one side never sees its star. Researchers must ask whether it has an atmosphere, whether heat reaches the night side, whether clouds stabilize the day side, and whether liquid water survives somewhere on the surface. Proxima Centauri b climate models have produced scenarios with permanent liquid water near the substellar region, although its real atmosphere remains unknown. If Earth became tidally locked, the end of sunrise would not produce one simple apocalypse. It would create a climate machine unlike anything in human history, a fixed stormy eye under the sun, a frozen hemisphere without morning, and an uncertain living world between them. The deepest twist is that permanent daylight can build reflective clouds, while permanent darkness can remain warm enough to keep its air. A world without days might still have places to live. Next, imagine changing not the length of the day, but the object above it. What if Earth had rings?